All right, so minor glitch there. Let me go back to screen share again. All right, so we're talking about anions. So fluorine changes to acquire a single negative charge. So now it has 10 electrons and still has 9 protons. How about oxygen? Oxygen has a tendency to gain 2 electrons. It has 8 protons. Once it gains 2, now we have 10 electrons and it becomes O minus 2. So now we begin to hit the naming rules. Okay, this is very much foreign language like. So things that are cations usually just are named as is. You use the name of the element and you just kind of put the word ion after it. So Na plus becomes or is called a sodium ion. Ca plus 2 is known as a calcium ion. So the anions are more conjugated when this is done. We have F minus. So it changes from fluorine to fluoride. O minus 2. Okay, this one loses all but basically the first syllable of the element name. So not oxygenide, it is just oxide. So if you look across the columns of the top of the periodic table, note we're kind of skipping over all the stuff in the middle where the transition elements are. There is a pattern. So hydrogen, alkali metals have +1 charges. Alkaline earth metals, +2s. Boron, aluminum, and occasionally the lower part of that column, +3s. Carbon, silicon, occasionally the stuff lower has plus or -4. It will depend upon what it is actually stuck to. Nitrogen, phosphorus, etc., -3s. Oxygen, sulfur, selenium, -2s. The halogens, -1s. And the noble gases, generally 0. One thing we can make a sort of a blanket statement about the transition metals is they're all positively charged, but there's a lot of variability. We'll come back to that. So if we're building molecules, you are creating ionic compounds. You want one or more cations combined with one or more anions, such that your net charge is 0. We're going to call these binary ionic compounds, basically 2 elements. So let's start with some sodium and some fluorine. So sodium becomes a +1 charge. Fluorine becomes a -1 charge. Since you have a single positive and a single negative, they will cancel each other out and there will be no leftovers. And you have a molecule that has 1 sodium and 1 fluorine in it. You're basically trading a single electron. How about magnesium and oxygen? So magnesium, being an alkaline earth metal, likes to be +2. Oxygen becomes -2. And again, we have an equivalence there, okay? 2 positives, 2 negatives, you add them together, there's no leftovers. You basically traded 2 electrons. What if you have things that don't match? Okay, aluminum likes to be +3, but oxygen likes to be -2. So there's a couple of different ways you can approach this problem. You can take the number part of the charge and use it as the subscript for the opposite element. That way we get Al2O3. But it's still premised on the idea that it really is based on the least common multiple concept. So 2 aluminums, okay, that gives you 6 positives. 3 oxide ions, that gives you 6 negatives. And that way you have an equivalent number of positives and negatives. So Al2O3. How about MGBR? All right, so you have to think about this. So magnesium has a +2. Bromine is a halogen, so -1. You can't just use a single bromine ion. You actually need 2, because you have to have the 2 negatives to cancel out the 2 positives that are on your magnesium. So as we're putting all of this together and making these binary compounds, most of the ones you will see are a metal plus a non-metal. Remember the staircase on your periodic table. And then we're also going to be talking about the non-metals. You can have a pair of them. Yes, truthfully, there are ways to combine 2 metals, but we're going to kind of pretend that doesn't happen. Even though in reality, it kind of sort of does. So how about the molecule we just made? Okay. So the first word of your name is your cation part. Hence, when you look at the list here, the magnesium has to be the first word of your name. Then remember, you are conjugating your second element and adding that IDE ending. So bromide, magnesium bromide. No, there is no indication that there are 2 bromines there. It is considered to be an understood concept. AlCl3, okay? Don't try to call it aluminum 3. Don't try to call it aluminum try something. It has to just be aluminum chloride. Back to the same concept. There is no indication in the name that there happen to be 3 chlorine atoms present. SRS, strontium sulfide, and then a name for the molecule that we recreated. Al2O3 is just simply aluminum oxide. No dyes, no tries, no Roman numerals. So, reminder, as long as you have what I will call a normal metal, meaning not a transition metal, along with a non-metal, the number of them, how many are present in the molecule, does not influence the name. All right, now we're going to kind of head on over to the transition metal idea. So pretty much all the transitions have kind of an either-or thing going on. We are mostly going to concentrate on, okay, it's called the stock system, but I also refer to it as the Roman numeral system. The Roman numeral indicates the charge. It does not tell you how many you have. It only tells you what the charge is because they are variable. So Cu plus 2, copper 2. Pb plus 4, lead 4. Sn plus 2, tin 2. And then we get back to the whole either-or concept. And there was actually a very specific reason why I spent a little bit of time at the beginning of the chapter talking about the Latin-based names. If you work in the healthcare system, they don't use the stock numbers, the Roman numerals at all. They always use the Latinized versions. So this is kind of why we went through them a little bit there at the beginning of the chapter. So irons come in +2s and +3s. You can call it an iron 2 or an iron 3. So iron 2 is ferrous. Iron 3 is ferric. Lead comes in 2s and 4s. So lead 2 and lead 4. Remember, lead used to be plumum as its Latinized version. So plumbus and plumic are some of the names that you're encountering here. So the older system, which I often refer to as the ich and us system, okay, it does have a rule or a pair of rules, but I will be honest and say that there's a lot of memory involved here because knowing the rules doesn't help as much as you might hope. The rules system says the one with the higher charge gets the IC ending. The one with the lower charge gets the OUS ending. But note, this kind of presupposes that you actually know what your options are. Like I said, there's a certain level of just brute force memory to this. All right, let's make some molecules that now involve transition metals. So we're going to take a look at these, and we're going to kind of start on the right-hand side of the molecule and kind of work our way backwards. So start with the anion portion. So FeBr2. Br, okay, halogen, has a -2 charge. We've got 2 of them. That must mean that in order to be making a neutral molecule, that your iron needs to be a +2. So we can name this both by the stock system and by the older system. Do not mix and match. So iron 2 bromide or ferrous bromide. If you use the ferrous term, do not put a Roman numeral in it. How about CO2S3? Okay, so this time we've got sulfurs at the end. So sulfurs are -2s because they are underneath oxygen. We have 3 atoms, so that is 6 negatives. If you have 2 cobalts, okay, then the +6 has to be divided in 2 equally. And you end up with cobalt 3 sulfide or cobaltic sulfide. Here's another tip. When you are looking at the Roman numeral system, most of the time, the Roman numeral is not the number of metal atoms that you have present. When we look at iron 2, yeah, there's only 1 atom there of iron. When we look at cobalt 3, no, there's actually 2. Okay. Much of the time, it does not match. How about iron? I mean, not iron, tin. So SNO2, we have -2. Okay, there's 2 of them. That's -4. So your tin needs to be a +4. We can call this tin 4 or stannic oxide. Here's another one to kind of look at. AuCl3. So more of the elements whose names are not matching to their symbols. So Au is gold. Because I have 3 atoms of chlorine, which is -1s, this has to be a gold 3 chloride. It is also known as auric chloride. So there are 2 transition metals in the bunch that do not have an either or. Those are silver and zinc. Silver is always and forever +1. There is no other option. Zinc is always and forever +2. However, you will often, or most of the time, see textbooks going ahead and kind of keeping along with the same path of putting the Roman numeral in even though there is not another option, if you have AgCl, sometimes you'll just see it referred to as silver chloride, but most of the more recent textbooks go ahead and throw that number 1 in there, even though there is no other option for silver. So we've been kind of ignoring the nonmetals to a degree. When you have 2 nonmetals in a molecule alone by themselves, no metals at all, here are the 2 rules that start you off. We have assume the first element is positive, even if you look on the periodic table and it looks like it's in a column that actually ought to make it negative. Okay, this has to do with a different kind of bonding that we haven't gotten to yet. And then you can assume that the second one is negative. This is the first time you are actually allowed to use a full-on prefix system. These are the prefixes that you may most often associate with geometry classes. We have mono, di, tri, okay, not quad. This one is actually the tetra. Penta, hexa, hepta, octa, nona, and deca. Yes, there are actually prefixes which mean something more than 10, but for general chem 111, 112, we are seldom going to see anything more than 10. All right, taking a look at a few of these. So carbon with 4 chlorines. So the first element, if there is a single atom, you are not allowed to use the word mono. I know that's weird, but it's kind of like this variation on the rules. We've got 4 chlorines. So carbon tetrachloride. Got to keep that IDE ending too. How about CO? No, this is not a cobalt molecule, or atom rather. This is an atom of carbon combined with an atom of oxygen. You are allowed to use mono if you have a single atom of the second element, hence carbon monoxide. They delete the second O to make it a little bit easier to pronounce. N2O5. So this time I've got more than one of my first element. I have 2 nitrogen, so it is dinitrogen pentoxide. Again, they're kind of deleting one of the vowels there to make it a little bit easier to pronounce. XEF6. Lo and behold, we have a noble gas that is part of a molecule this time. Not common, but does occasionally happen. Xenon hexafluoride. The hexa is your indication that there are 6 fluorine atoms in the molecule. OF2, oxygen difluoride. Yeah, we're not really used to seeing oxygen as the first element in a molecule, but again, it can happen. And we have an assumption that it is behaving as if it were positive for this scenario. All right, so now we're kind of up to the end of the binary compounds, the ones that have just 2 elements. We are now going to embrace polyatomic ions. So this is actually not a textbook description, but I think it is the best description I've run across. Polyatomic ions are several atoms bound together that behave like a single element and have a charge that is attached to the whole group. So such things as SO4-2, sulfate, or OH-, hydroxide. On page 62 of your textbook, not your lab book, there is a table which you basically need to memorize. There are actually way more polyatomics that are on that table. if you are watching this because you are working on your nomenclature lab, remember that there is an entire page in your lab book that is primarily devoted to polyatomics. So yes, there are many, many more than the ones that are on page 62 of your textbook. So one of the things that is true about polyatomics is a vast number of them have oxygens attached. 1, 2, 3, 4, occasionally more. They are called oxyanions, and a whole lot of them come in sets. Things that have a set of 2. This kind of goes back to rules do apply, but technically speaking, the rules aren't as helpful as you would actually like. Smaller number of oxygens, ITE ending. Larger number of oxygens, ATE ending. Lest you think, oh, if I see 3 oxygens, it automatically ought to be ITE. No. So NO2 minus nitrite, NO3 minus nitrate. Then we flip over to sulfur ones. SO3, that one's sulfite. SO4, sulfate. So there is a lot of memory involved here. Back to the recommendations. Flashcards or memorize, okay? Using the drill modules that are available on Memrise is something that is often popular with students. How about the sets of 4? So sets of 4 are a little bit more expanded. The center is actually partly the same. We have the ITE and the ATE. But the lowest number of oxygens has a prefix of hypo, because hypo means under. And the highest number of oxygens has a per out in front. So all of the halogens are capable of doing this. I picked on chlorine, but you can do it with fluorine, bromine, or iodine. Some of these are more common than others. So ClO minus. So note we have a single oxygen, hypochlorite. 2 oxygens, chlorite. 3 oxygens, chlorate. 4 oxygens, perchlorate. You can also have things like hypobromite or periodate. Yes, it's pronounced slightly differently there. How about if we start plugging them into molecules? Okay. The rest of the rules haven't gone away. Is the metal at the beginning a regular metal or a transition metal? CaOH2. Note, my OH is inside its own set of parentheses because I have more than one of them. Hydroxide has a single negative charge, so I am going to call this calcium hydroxide. Do not put a di in there. It is not dihydroxide. You can't put extra prefixes into polyatomics. Calcium also has no Roman numerals because it is a regular metal. Na3PO4. We only have a single chunk of PO4, so there's no parentheses involved. I do have 3 atoms of sodium. But this goes back to that idea of having multiple atoms doesn't affect your name. Sodium phosphate. Please do not endeavor to name this like totally inexplicable and wrong things like phosphorus tetraoxide. Okay, that's not a thing. How about a transition metal? FeSO4. Okay, this is what's in your vitamins if you had vitamins with iron in them. If you read the back of the bottle, it won't say contains iron 2 sulfate. It will say contains ferrous sulfate. Remember I told you the medical community kind of ignores the stock system. Why is it a 2? Because your sulfate is worth -2. Therefore, the iron needs to be +2. Couple little actual variants here. You will see listed on your polyatomic table something that is known as peroxide, which is 2 atoms of oxygen with a -2. The only way it can be qualified as a peroxide is if it's attached to a metal, usually a metal from group 1. Hydrogen is in that column. It is at the top of the alkali metals column. So H2O2 is a valid compound, hydrogen peroxide. Last set of rules. Acids are things that when you dissolve them in water, they release a hydrogen ion. So if you see a molecule and it starts with a hydrogen, providing it's not a water molecule, it's pretty close to a guarantee that it is going to be an acid. So then the next question part of this is, does my molecule have any oxygens? If no, you need both a prefix of hydro and a suffix of ic. So I gave you a couple of examples here. Hydrochloric, HCl. There's no oxygens involved. Hydrocyanic. The CN is a cyanide polyatomic, but it has no oxygens in it. Now we go back to IC and US systems again. So again, rules are not as helpful as you would like, but if the anion, the things that came after the hydrogens, used to end in ITE, when you make it into an acid, it has to become an OUS acid. If you had an ion that ended in ATE, it changes to IC. So sulfate becomes sulfuric acid when you put the 2 H's in front. Sulfite becomes sulfurous acid when you add the 2 H's in front. They look similar. There's a super big difference, okay? Sulfurous acid, you could stick your finger in the beaker and it really wouldn't do anything. You do not want to stick your finger in a beaker full of sulfuric acid. There is a significant difference in its power. So all of this covers all of the basic rules. Let me see if I can actually invoke the whiteboard. I have one more thing to touch on here. Let me do this. Okay. I'm using my home connection to do this, so I actually haven't seen this version of the little dots on the whiteboards before, but anyway, we'll go with it. So one other thing that is also included in your nomenclature lab. So if you're watching this for assistance with your lab, this is also something that is included with that. Sometimes you will see a molecule that starts out looking like a fairly regular molecule, and then it will have a dot or an asterisk, and then it will have water molecules attached. So for instance, this has a Ca, 2 Cls, and 2 water molecules attached to it. So when I name this, okay, name the first part in the beginning without paying attention to the waters. So I am going to have calcium, because I have a single atom of calcium there at the beginning. Okay, I have 2 chlorines attached to it, so this then becomes chloride. Okay, those water molecules make it a hydrate. And yes, there is a paragraph about this in your lab book. In your textbook, it's in a different spot. It's like not in chapter 2. We're going to call this dihydrate because we're going to use the same prefixes that we used for the non-metals, but we're going to attach them in front of the word hydrate. So calcium chloride dihydrate indicates to you that first you have an atom of calcium or a molecule of calcium chloride, but the dihydrate is the indication that there are 2 water molecules attached to it. We're even going to do a full and complete lab that is attached to the idea of hydrates. We are going to dehydrate things and figure out what number of water molecules used to be attached. So we're going to dive into this more in the upcoming weeks. So as I said, this is a duplicate recording. I am posting it both to my lecture because it covers the remainder of chapter 2 since I am not on campus on Monday, June the 5th. But I am also posting it to my lab since I don't have a complete overlap of students there. I have a few people who do not have me for lecture. This covers all the basic rules for nomenclature. It should not only allow you to begin working on your homework for lecture, it should allow you to have enough information to begin work on the nomenclature, all 6 pages of it, of your lab report. On Wednesday, when I am on campus, I will definitely spend a lot of time, hopefully, answering some questions if you have kind of uncertainties about how you are supposed to apply certain types of rules.